just as a reminder, I do record any and all lecture sessions, guys. I do that and post it to my YouTube channel. If you miss time in class, you can always go back and watch what you missed there. So we left off last time talking about standards and why standards are a thing. So why do we have standards and standard committees? What do y'all think? What? So you get the same results. So you get the same results. So what? Why do you need the same results?
So you can be accurate.
So you can be accurate.
You probably get the most effective use out of the robot.
Most effective use. A lot of it's just so that you have interchangeable parts. That is like the main biggest reason most people conform to a standard is because you want to have the ability to something breaks, you can fix it. Any of you have a really older model car? Yeah, how hard is it to find parts? Sometimes. But if it's a really common current car, how easy is it to find parts? It's very, very easy. You have anything from the 2000s forward, generally you can find parts for it. And I say generally. I do not say that you can always find parts. But that's why you standardize. You are trying to make sure that parts are interchangeable. If somebody can't find parts for one thing, they can find parts that are similar enough that you can still keep working on what you've got. Does that make sense? Okay. So it's all about having interchangeable parts because up until about the 19th century, up until about mid 1800s, you really didn't have interchangeable parts. Everything was what? Everything was custom. I don't care what you bought. If you had a rifle that was a mass-produced rifle, and I'm saying that because I know people like to go hunting, or you had it for self-defense. Because back then we actually still had bears in Alabama. Nobody wants to tackle a bear. Not even the little black bears that kind of roam around here. Pretty sure we had mountain lions too. And at least you have a bobcat. Nobody tangles with those. Anyway, digress. But even if you got a mass-produced rifle, same one as what your buddy had, or you had neighbors that all had the same rifle. If yours broke anything, how did you fix it? No, you really couldn't because the parts were not interchangeable. Had to go buy a new one. That's exactly what it was. You either had to go buy a new one or you had to go to somebody that had a specialty in it. So if you had a missing nail or you had a missing firing pin, you would have to go to somebody like a blacksmith and say, hey, look, this is what I had. Can you make me something that is similar enough that I can repair my rifle? Most of the time, the answer was maybe. Wouldn't work as well as the original, but you could at least get it replaced to some degree. So we now have standard committees that allow us to create a standardized parts. Why? Because it makes it to where you break something, you can fix it. Okay? That's the main reason. If you break it, you fix it. So, having talked about that, let's move on to fluid power systems. Okay? First of all, what do we mean by a fluid? That seems rather ambiguous term, and most of us, I know what you were thinking of when you hear the term fluid. But what is fluid? What do we mean by fluid power?
So
Most of it tends to go towards them.
A machine that is run off of some type of fluid, whether it's oil.
You tend to think with fluid, the word comes to mind as liquid. Yes? But we don't mean strictly liquid power, because air is known as a fluid. Now, I know it sounds weird to say air is a liquid, but it is.
Miss Bush, I joined the class.
Okay. So air is a liquid in and of itself. It is not a liquid, but it is a fluid. Any of you ever play with dry ice? Anybody ever play with the vapors that come off of dry ice?
Yes, ma'am.
Okay, so you have vapors that come off dry ice, and if you put them in a container, you can actually move it from container to container, and it flows like a liquid, but it's air. So air is, a fluid is anything that can flow and takes up space. And let's face it, we all like having air taking up space, right? Because we all get to breathe. So most of the time you think fluid, you think of liquid. But in this case, you're not just thinking for a liquid, you're looking at liquids and gases. Okay? So the most common ways we transmit power, because we have to move power from one thing to another, otherwise nothing works. So you have electrical, mechanical, and fluid. Now electrical is a very common one. Why? Because I think most of the world nowadays tends to run some form of electricity. Okay? Just about anywhere you go, there's electricity of some caliber or another. Okay? Most plants that you go to, any place that does manufacturing, I will not say all of them, because there are exceptions in the world. And by the way, if you ever are taking a test and you see the words all or always, you might want to read those carefully, because generally those are supposed to be a question saying false. But there is no absolutes. So most plants have fluid power of some sort. Most of them have at very least pneumatics. Why? Because pneumatics is clean, it's easy to run, and you can get it from one place to another, and the transmission of power is very, very easy. Liquids are hydraulics, and the problem with hydraulics is what? It'll leak at some point. It gets messy. It's all over the place, and you're dealing with possible flammable liquids. I won't say they're all flammable, because things like oil, gasoline, kerosene, things like that, all of that is kind of actually hard to light off if you start trying. So mineral oils, or oils in general, are often what we use in liquids, in hydraulics, mostly because they're easy to access and they flow really well. One of the best things about using hydraulics is that they self-lubricate, which means that if I have pistons and cylinders, I don't have to worry so much about their lubrication schedule as I do if I work with compressed air. Compressed air tends to be something that dries out all other components. That's just part of the problem of it. And there's a lot of things that you have to make sure you've got going with your fluid power when you're dealing with air. The least of which, here in Alabama, what are the two biggest issues we have in the spring and summer? Pollen, and makes it miserable to go outside in summer, and makes it to where you have to have gills to breathe. humidity. Makes you feel like you're in a sauna factory on the sun. But we tend to use compressed air as the most common gas. Now, that's not to say that you can't use something like pure oxygen, hydrogen, helium, nitrogen. All of those are common gases as well. But the most common way we use pneumatics is just to use an air compressor that sucks in the gas around it and then transmits that power to other parts of the plant. Okay? So pneumatic systems, there's a lot of things we do with pneumatics. Pneumatic tools, where do you see those? Just about anywhere we want a little extra power that we can't do with muscle power, right? Construction sites use them. That's one of the cooler ones. Construction sites use them a lot. And what's come about in the last few years is that they've now figured out how to use pneumatics to lift heavy objects and make it where instead of having a 10-man team to push it, you can use only 2 to 5 guys and move something that can weigh several tons. And what they do with that is they create an air cushion up under. Anybody ever play air hockey? Everybody's played air hockey before. How does the puck move? It's air on a table. They figured out how to use that same thought pattern to move extremely heavy objects with like barely a finger push. Think about that for a minute. Using pneumatics, who would have thought to use pneumatics to move something like that? It takes a lot of air pressure to push against whatever you're trying to move. But once you get it lifted, it moves as easily as a air hockey puck across the table. But you have pneumatic tools, things like impact wrenches. Isn't that how you take the lug nuts off a car? A very quick way. Zoom, zoom, take them off, take them all off, replace the wheel and tire, move on to the next one after you put them back on. You have linear motions that are available with this, as well as rotating motions. Rotating motions, you should be familiar with. Linear ones, if you've ever seen pneumatics being used with pistons and such, that's your linear motion. Okay, so fluid power is the use of fluids under pressure to generate, control, and transmit power. Hydraulics is liquids, pneumatics is gas. Now, some of this is a bit of a misnomer. Because yes, you can pressurize gases, you don't really pressurize liquids so much. Anybody know what happens if you overpressurize liquids? You're gonna blow a seal. What? You can bust a pipe. You can blow a seal. It's really nasty stuff. Give you for an example. I have an older brother, and my dad lent him his truck one time for a long time. Now, understand one thing, that is, my brother's not always the smartest man in the world. He decided one day that the truck was low on oil. So he put about 5 quarts in it. The truck takes 2. He blew every seal in the truck because of that. So hydraulics don't like a lot of force. Okay? They like a little bit of force. They can tolerate it. It makes them move. Excuse me. Speaking of allergies.
Bless you.
Hydraulics don't like to be high pressure. If you put too much pressure on hydraulics, it blows every seal you've got, and you just end up with a giant mess. What's worse is that this particular mess can be kind of a kind of a hazard, either chemically or environmentally. So it's one of those things you have to really kind of be careful with. But the good thing about hydraulics is that it takes very little to transmit power with it. Hydraulics are pretty much known as the biggest workhorse of industry. Why? Because with hydraulics, you can move just about anything with hydraulics. They're that powerful. Think about this. What's the biggest truck you've seen on the road? How does it move? How does it stop? Now it has what's called air ride assist on a lot of these, just like on a Turner bus. All that is mostly suspension. What stops those trucks are hydraulic brakes. You're talking brake shoes that are not that much smaller, not that much bigger than a big truck's. Okay? They're not that much different than what you would see on a road vehicle. But they're able to stop something that might have a couple tons hauling behind it. That's why hydraulics are the workhorse. They get it done. It's also why you've not seen hydraulics disappear very much. We use them for just about everything. Every industry is touched by it at some point. Why? Because at some point when you need the power, it's got the power. Okay? So here's some terms that you're going to want to write down or at least kind of memorize. So let's start off with force. And no, I am not talking about the force. We're talking about force. Sorry, stupid Star Wars joke. Showing my geek. So this is anything that causes change. Okay? It either is the change or changes the state of something else. Okay? So Newton's laws. That's kind of what we're following here, right? I can't remember which law it is, but it's that every action gives you an equal and opposite reaction. I believe that was either the first or second law. But that's basically what force is. What you're doing with force is making something happen. It's going to make it's a way to create change. Okay? We're going to be talking about area. And most of the areas we use when it comes to hydraulics and pneumatics, unfortunately, are not square. So how many of y'all remember how to find the area of a circle? Pi r squared?
Pi r squared.
Yep. There's a lot of them out there, guys. There are some easier ones, though. We'll go over a few of them. So we will be finding area. Yes, we're going back to that. But I'm trying to make it easy. Weight is how you determine what something is as far as heaviness. Density, how crowded something is. And then you have pressure. Now, most of the world does not use PSI. I know, that's one of those things of, wait, what? Huh? That's cars. That's that you're talking kilometers per hour. But what we have here are things like newtons and several others that we're going to be talking about. Why? Because the rest of the world has moved on to the metric system, and us, and I think 2 or 3 other countries are the only holdouts still that are holding on to imperial. Why we continue to hold on to imperial, I cannot fathom at this point, but it is one we have held on to for many years. Believe it or not, the U.S. government was initially trying to push for a full changeover. And at one point or another, that full changeover just kind of died. They realized it was just going to cost too much money to do so. So we are one of the last countries standing in the imperial system. I think one of the other ones is Myanmar, and there's another small country I can't remember.
You teach the same class at the morning time?
Hmm?
You teach the same class at 8:30?
No. I teach robotics at 8:30 in the morning. And I teach DC on Tuesdays and Thursday nights. All right. Everybody good? Anybody need a minute? And guys, these slides are out there on Blackboard if you think you miss anything. Okay. Everybody good? So units. No, you don't have to write this down. This is just how it was working these days. As far as units go, the U.S. customary system, which is based off of very weird measurements. I mean, seriously, a foot is 12 inches, but a yard is 3 feet. Who came up with that? Who in their right mind? Seriously, think about it. So yeah, it is still used in the USA, Myanmar, and Liberia. 3 countries are holding out onto this. Some of it is still used a little bit in Great Britain, but most of them have moved over into the international standards, which are based on the kilometer, kilogram, things like that. So the imperial system is very similar to the U.S. customary system. They do have some measurements that are a little bit different than ours. But like I said, for the most part, those two systems are dead. Why? Because if you really stop and think about most of them, they make no sense at all. Seriously, look at the different tables and stuff and ask me how that happens. So most of the world has gone on to the International System of Units, otherwise known as the metric system. Why? Because it's all based on 10 and it makes sense and it's very easy to calculate from anywhere in that point. So we're talking pressure. This is the amount of force exerted on an object by the area. So any of you have ever taken any of you have ever taken DC or intro? You know what a circle means. It means we got a formula. So force is equal to area times pressure. Force is area times pressure. And that is a hard and fast one that is true no matter what. Okay? So there's 3 types of pressure that we measure. Okay? So first of all, does anybody know what the pressure you feel at sea level is? Anybody at all?
The pressure is 14 point.
At sea level. Now, the reason I'm saying at sea level does not mean that it is not a universal thing you're going to feel. If you go up to the top of Kilimanjaro or the top of Everest, not so much pressure. But level, you experience 14.7 psi. That is the true atmospheric pressure. Okay? 14.7 psi. Now, what that translates to in newtons or anything else, I don't know off the top of my head. I know 14.7 because I've drilled that into my own head sometime. At some point. You have gauge pressure. You have atmospheric pressure, and you have below atmospheric pressure or vacuum. And actually, list it here. It's 14.7 psia, 101.375 kilopascals absolute, 29.92 inches of mercury, or 760 millimeters of mercury. In other words, all of it just saying that you experience pressure at sea level. The higher you go, the less pressure you feel. Okay? Because basically the whole atmosphere is pressing down on you because gravity is holding the atmosphere to the earth. So thus, the closer you get to the sea level, the more pressure you experience. We're not going to talk about what you feel under sea level because that's a totally different thing. Because the weight of water plus the weight of the atmosphere starts adding up really quickly. That's why at the bottom of the pool, you feel more pressure and more weight than if you're laying at the top of the surface. Does that make sense? Okay. Barry, go ahead and finish out that explanation because otherwise all of y'all are looking at me like I'm crazy. Anyway. So below atmospheric is a vacuum or negative pressure. Okay, everything starts pulling air to it. All right. Probably would help if I had my mouse on the right thing. So pressure units, there's a lot of them. You have pounds per square inch. This is the basic and most common one here in the U.S. Okay. Unfortunately for us, the rest of the world is not us. So most of them do not use PSI. They use and there's a lot of other ones they can use. A lot of other ones. To begin with, you have Pascal. That's dealing with newtons exerted on 1 meter square. Okay. You have a kilogram force per square centimeter. And I know there's several different ways you can say centimeter. I've always said it's centimeter. So if you say it differently, I'm sorry. Kilogram force per square centimeter, you have bar. Now that one you might have heard of or seen if you look at a pressure gauge. Some of them do have bar on them. Or you might have seen KPA. So you might have seen KPA. You've probably seen bar. Torr, not so much. Inches of water, probably not very much. Inches of mercury or millimeters of mercury, yeah, those exist. And they are used. And head pressure, I'm not sure quite where you would use that, but it is one that is out there. Okay. And here's some different conversions. Yes, it is quite a few different conversions. The main one we'll be using in this class is PSI because we are in America and we still use PSI here very frequently. The other ones you might want to start looking at just to have in your head because they do exist outside and we do have gauges here that use them. Would be the Pascal, kilopascal set right here, or megapascal is what that one is. is one that you'll commonly see. And you might see millimeters of mercury. That's the one with the Hg to it. But bar and Pascal are the ones that are most commonly used on gauges you might come across here. I said that we'll be mostly using PSI in this class. Just a good thing to have known on how to calculate these. So PSI, again, is the most common. You have this one over here that is 100 kilopascal. It has a PSI scale and it has bar. I'm sorry, bar is 100 kilopascals. It actually tells you how to read it. But you also have the PSI scale. Gauges, how many of you, I'm assuming all of y'all drive. So on your car, what do they have as the speedometer? And most cars, I don't know if they have them on all the cars, and especially not the new ones these days, but at one point, all cars had miles per hour and kilometers per hour. How did you tell the difference? Same way you tell the difference here. They will give it to you either in a different color, or they just put it on the inside of the gauge instead of the outside. This one is pulling a vacuum, and it's looking at inches of mercury, or again, it's looking at bar. Okay? All right. Sorry. So even with the blood pressure, it's given in millimeters of mercury, not PSI. Okay? Or it could even be given in inches of mercury. All right, so talking about force. So this is any actions when unopposed will change the motion of an object. In other words, an object at rest stays at rest, thank you. An object in motion stays in motion, unless they are acted on by a secondary force, I guess is how that finishes. Now, it sounds great in your head when you start talking about all this, and then your brain and your mouth have a disconnect. Sorry. But yes, an object at rest stays at rest. An object in motion will stay in motion unless they're acted upon by an outside force. In this case, we are creating the outside force with force. So a couple different ways that you measure this. You have the Newton, which is the scientific or standard unit of force that's acting on a 1 kilogram object. Causes an acceleration of 1 meters per again, brain not running. Over 1 meter divided by second squared. You have, I'm not even going to try and pronounce that today because right now I don't know why my brain's not pronouncing these right. But that equals 1 force gram object. I'm sorry, the force of a 1 gram object would cause an acceleration of 1 centimeter over second squared. Yes, I actually said something right for a minute. And then you have pound force, which is what we use here. Generally, we're using pounds of some sort to make something move, right? So how do we measure weight here? We measure it in pounds, which is why you have PSI. So work and power. For those of you that have taken my intro and DC classes, how do we generally measure work? In electricity, we measure it as as power. If you're measuring power, electricity, you measure it in watts. In this case, we're doing a different kind of work. So this is a more physical work, less electrical work. Work is done when force is moved some distance. Okay? So thus we're going to measure, I'm trying to condense all this so it's not as repetitive. So work is force times distance. The power that comes from it is work divided by time, or force times speed. Okay? We're talking a lot about speed. Why? Why does speed matter? Hmm? Speed is a output of force, yes. When you get force, force is making something move. When you move anything, that's going to have to do with speed, right? Okay. So a couple different formulas. So you have work is equal to force times distance. Velocity is distance divided by time. By the way, velocity is another term for speed. You want to use that one instead. Power is work divided by time, or force times velocity. So force times speed. Very good. All right, let's move on. So we heard about the name Pascal the other day while we were watching the video, right? So who is Pascal? Well, he's some dude that decided he was going to study fluid dynamics. He wrote the book on it, actually. And his law states pressure exerted on a confined fluid is transmitted undiminished in all directions and acts at right angles to the containing surface. Somebody break that down for me. And yes, I'm forcing you to participate. Somebody break it down for me. What do you think it means?
When the pressure on the fluid expands everywhere.
A pressure on a fluid expands everywhere. Pretty much, yes. Think about blowing up a balloon. Okay? When you blow up a balloon, where is the most force exerted?
Everywhere.
It's over the whole surface of that balloon, right? The inside surface of the balloon, you're exerting force, which is pushing the air into that balloon and forcing it out so you blow the balloon up, right? That is exactly what this is saying. Okay? So it is transmitted undiminished in all directions and acts at right angles to a containing surface. In other words, if you were to blow really hard into a bottle or a balloon, it's going to expand and all the air or fluid is going to try and push really hard against the confining surface areas, right? Because what you're doing is pushing air or fluid through the very middle of it, which means it's pushing away. Okay? So when pressure is applied to a confined fluid, same thing. I need to go through these slides. All right, so this is essentially the same thing I was talking about. If you imagine the outside of this, not so much as a piston and cylinder, but as you blowing into a balloon. This is exactly what you would see. The air is trying to move everywhere and trying to escape. We are confining it. So a confined fluid, see, this is why you cannot crush a bottle that is still full of liquid. Can you crush a bottle full of air? Yeah, very easily. Crush one full of a liquid? Not so easy, right? Think about trying to crush a can. If you have a can of soda and an empty can of soda, which one's easier to crush? The one that's empty. If you try and crush the one that's full, you're going to have an issue with that, right? Because no matter how hard you stomp, are you going to crush it? No. Not until you break the seal and all of a sudden everything goes everywhere. Right? That's Pascal's law. So force is equal to area times pressure. Those of you that have never dealt with one of these, this is times, that's divide, that's divide. So if I'm looking for area, I divide force by pressure. If I'm looking for pressure, force divided by area. If I'm looking for force, area times pressure. It's a really, really easy way to work with these formulas. Okay? Really easy way to work with these formulas. And by the way, guys, I don't know if I told y'all this yes on Monday. But I'll go ahead and say it again now. Fluid power data books. You want this. Why? Because on page 9 of the fluid power data book, there's lots of formulas, including one that's for force is equal to area times pressure. And you get to use this on your tests. So the sooner you get one of these, the better off it is. Yeah. Yes. You should be able to get it at the bookstore. So sooner rather than later on those, gentlemen. You want them sooner rather than later because sometimes I'm even nice enough to provide you page numbers that you want to keep up with. All right. So force, area, and pressure with their matching units. You have pounds, newtons, inches squared, meters squared, millimeters squared, PSI, pascals, and megapascals. Okay. All right, so Pascal's law of pneumatic leverage or hydraulic leverage. So with this particular one, if I had a secondary piston on the other side, and I put pressure on that piston on one side, what's going to happen to the other one? It's going to go up. It goes back to that, how do you lift a 2 to 4 ton car off the ground enough to change a tire? Well, you might have a very small piston in your car jack, but you have a larger piston on the other side of that car jack. And eventually, with enough upper body work, what do you get? Car lifts about an inch or two off the ground, just enough for you to, just enough for you to change the tire and move on with your day. Okay? Because that is what is called force multiplication. So pressure developed in one place is used elsewhere and allows forces to be multiplied through the use of piston surface areas. Force multiplication is probably the biggest part of why we use hydraulics and pneumatics. With hydraulics, we see it in some very big machinery, right? Everything from dump trucks to backhoes to, is there a piece of machinery out there that does not use hydraulics in some form or fashion? Not that I can think of. Even bulldozers use it. Why? Because eventually a bulldozer has to do what? They lift that bucket, they shake it out, make sure there's no dirt or anything in it, then they drive back and they do it again, right? That is their purpose. Well, how do you keep that bucket from getting knocked up and down all the time by giant rocks? Use hydraulics. Lock it in place. Use hydraulics to lift it so that you can knock things out of it. Doesn't matter what machinery you can think of as far as construction goes, at some point it uses hydraulics. Because that force multiplication means that, I'll put it to you this way. Think of the big cranes they use to move, let's say, steel girders so that they can build high rises. Y'all know what I'm talking about, right? Those 100-foot cranes that stand up, or the ones that you even mount to the top of a building next door so you can swing things around. How do you think they move that stuff? It's all hydraulics. Can you imagine what the mechanics of it would be if we had to do that without hydraulics? What the size of the gears would have to be, the size of the ropes and the pulleys and everything else, and how complicated it would be. And the more complicated you make something, the more easily it what? The more easily it breaks. Everybody follow? I mean, that's probably the worst thing about the more complicated systems you create. The more ropes and pulleys you have to create to help with mechanical advantages, you would have to make it so complicated that probably after 1 or 2 uses, you would be having to repair it every 5 minutes. So instead, we use hydraulics, and we get the job done. All through force multiplication. All right, so Pascal's law. Because I have an area of 1, I don't think that was supposed to be AN, I think that was supposed to be meters squared, and that's what we're going to change it to. I will say inch squared. I think somebody forgot the I. So an area of 1 inch squared, we're going to be looking at an area of 5 inch squared. Okay? Now, the problem with force multiplication is that there is no free lunch, right? Can I use this smaller piston to lift the larger one? Oh yeah. But if I want to move that larger one 1 inch, how much am I going to have to move this one? You have to move it about 5 inches, right? Or in this case, as far down as you can get it. Because there is no free lunch with any advantage. To move 1 inch there, you have to move 5 inches here. However, if I was trying to move it the other way, I would only have to use 1/5 of an inch on that side to move whatever's on this side. So, in other words, think of, anybody ever used the giant airbag things that they have at pools and stuff to try and launch something off the other end? Y'all know what I'm talking about? Think giant air cushion. And you as one person can launch somebody off the other side. Basically, that's how that works. Because the air you force away transfers to the other side, and if you weigh more than them, you launch them into space. Hopefully into a body of water. Because otherwise that would really hurt to land. That's why that works. That is why Pascal's law works, is because by pushing on the small end, I can move the large end. I don't move it very much, but I move it. If I push on the large end, I can really launch the smaller side though, right? It doesn't take much force to do so. We'll come back to this in a minute. All right. So the good thing about fluid power is generally that work out is equal to work in, and power out equals power in. You can get a lot of output force for the input force you give, so on and so forth. It's all the same things I've been saying for the last 5 minutes. Okay? Now, before we get to this point, so part of what we can do looking at force multiplication is we can actually figure out ahead of time what something's going to do. So one of the first things we have to do is what? Looking at any of this, we need to know what our area of our cylinders are, which I think those are already given to us in this. Yes? We have our force, which is 100 pounds. So what would our PSI be, first of all? I think it's rather impressive I'm doing this well with a mouse. So what would our PSI be? Well, our formula is force is equal to area times pressure. I'm looking for pressure, what do I do? Force divided by area. So I would take my 100 pounds divided by 10 inches squared, and my PSI should be what? 10 PSI. Now, here's the funny thing about force multiplication. That 10 PSI does not just apply to this side. Guess what it applies? It applies to the whole system. It applies to the whole system, top to bottom. So that 10 PSI skates all the way over. So what should my force out be? Since that's a very small space, I'm going to kind of put this in there. What should my force out be? Area times pressure, giving me 50 times 10, guys. 500. 500 pounds. So with only 100 pounds, I'm able to lift 500 pounds. What kind of an advantage is that? It's an advantage of 5. All right. With 5 pounds, I can lift 1/5 of the other side. Anyway. So if I put another 5 pounds here, I would be able to lift even more. But, yeah. Let's see. Where did my mouse go there? So with 100 pounds, I lifted 500. If I was to cut that down to 50, this would go down to 250. Long as that pressure did not change. Okay. So the output distance would be 1/5. So that goes back to how many times do I have to hit the car jack before I actually get enough off the ground to change the tire? Right? I'm working myself to death on one side of the car jack. How much am I actually getting out on the other side? Not that much. Very little. So if I pump it 5 times and I'm pumping, let's say, quite a bit, my output could be 1/5 of what my input is. That's exactly what we're looking at over here. This is 1/5 of what is coming out on the other side. Now, in some cases, that's good. Some cases, just stinks to have your car with a flat tire. You can't go nowhere. All right, so looking at the output force. Now, this one is particularly tricky as far as a problem. And that's because what? We're told this is a 3-inch bore. Now, the bore means that's the cylinder head. But is that the area? No, that's the diameter. So guess what we have to find? We have to find area. There's a couple different formulas you can use. If I can find the right book, I've got them. That one's mine. Jeez. One of those, I write stuff down in certain ones and I don't write it down in others and I always forget. So there's several formulas for the area of a circle. And I might want to write these down. One is your typical pi r squared. You also have pi times the diameter squared divided by 4. Or you have an easier way. Diameter squared times 0.785. Okay? Diameter squared times 0.785. Now 0.785 comes from dividing pi by 4, if I remember right. Since most bores are given not in their radius, but in their diameter, I've often found this one is probably the fastest way to do that. So 3 squared is 9 times 0.785 is what? Anybody with a calculator? 7.065. So what about one of the more traditional methods? What do we get? Somebody do pi r squared or pi diameter squared over 4? At the very least, you have calculators on your computers and or your cell phones. Okay, which is? So you said 3.14 times 9 divided by 4. It should be the same thing. It should be 7.065 or close to. I just wanted to prove that that works because a lot of people look at me and go, no, there can't be another formula. There is. Hmm? Divided by 4. This is formula 1. This is formula 2. Let me erase my little marks around here. This is formula 3. Formula 3, to me, is the fastest, easiest way to solve these. Area. I have to say there is a slightly faster way to find the area with these books. It gives you the area of the cylinders. Starting on page 15. If you look for hydraulic cylinder force, you have the piston inches in diameter, piston diameters in inches, the rod diameters, and then you have effective area in square inches. So, yeah, the answer should be close to 7.06, and then anything after that, kind of whatever you end up rounding to. But if you cannot get one of the books, these are the 3 best formulas for finding the area of your rods and cylinders. Anyway, so a 3-inch bore, the area is 7.06, and we'll say 5 at the end of that. So 7.065 inches squared. And that is a terrible square, but that is what that is. So before we can move forward, probably the next easy thing to find would be the next thing we need to find is the effective area of the 5-inch bore. So what would be the area of that 5-inch bore? So using one of these 3 formulas. What you looking at? Okay. Yeah, it's 19.625 or yeah. 19.625, or if we round up, we'll just leave it at 19.63. If I can write. So 19.63, we'll leave it at that. We'll write it down over here. I don't have the space to write inches square on that, so that is supposed to be inches squared. So what's the next thing I need to find before I can find my force out? I have my force in, I have my area for the force in. What's the next thing I should find? Pressure. How do I get pressure? Force divided by area. Yes, force divided by area. what is my PSI? What's my pressure? Huh? So it should be 200 divided by 7.065. 28 point what? So 28.3 PSI. Okay. What does that mean my force out will be? So I would take 28.3, multiply it by 19.63, and it gives me what? £555. So 555 point what? We'll just put 0.5. So 555.5 pounds. Okay. Any questions on that, guys? Because I'll go ahead and tell you now, on your first test, there's going to be a question very similar to this. And it's going to require that you do many of these same steps. I'll go ahead and warn you now. Okay? So here's your math again. Area 1, you have 3 squared times 0.785, because 0.785 is pi divided by 4. Okay? So 3.14 divided by 4 is 0.785. So I don't know who figured that out at once upon a time, but that is how that rolls. Yeah. So 3.14 divided by 4 is 0.785. So 3 squared, or 9, times 0.785 should have given us roughly 7.065 inches squared. To find pressure, you divide your force by your area, 28.3 psi. Your area 2 would be that 5 squared times 0.785, giving you 19.625. Force 2 is 555.5 pounds. And ta-da! Everybody good? Any questions on this problem? So any questions on this problem or the answers given here? No? All right, moving on. So pressure on the 1 inch squared area is transferred equally throughout the system. And that is what we were just talking about improving. Okay? Pressure on the 5 inch squared is 5 times greater, but the speed and distance is 1/5 that of the smaller piston. So in other words, Again, it goes back to force multiplication. How many times have you got to crank on that jack to get it to move? Have any of you ever tried to use an engine hoist? Yeah, don't. It takes forever to use one of those things because you're literally sitting there pumping up and down trying to get that silly thing up and to lift an engine. I mean, that's not even to lift the engine. That's just to lift the arm of the crane. I've done it before. My dad's got one, and it is not one of those things I like messing with because that thing is heavy. Your arm about dies while you're trying to crank the crane. Because here's the weird thing. You know how on some things you can sit there, grab it, and push it up, and it just stays there, right? Yeah, with hydraulics and pneumatics, no, you can't do that. The pistons don't do that. They don't like it. They don't want it. So you've got to sit there and physically crank on it until you get it to the position it's supposed to be in before you can do whatever you're about to do with it. It is a seriously frustrating, aggravating, and pain in the rear part about it, but that is hydraulics. So let's talk about how flow occurs. Anybody go to the river at all? Everybody been on a river? Seen a river? So there's two types of flow. And the best visual I can give you is that of a river. Okay? I'm going to erase our formula here. I can write it down later again. So if you've ever been on a river, you know that whenever you've got a nice straight path for it to flow, how does it flow? Is it chunky, rocky, you're finding water spraying in your face? Or is it very smooth, almost glass-like? It's a very smooth ride, right? But if you start coming around corners, what happens to that flow? You get disrupted. That's whenever you generally find things moving faster in one place, faster in another. You might find a slow spot somewhere. That's where you get rapids and rocks, right? So those two types of flow have names. A very smooth flow, like your smooth section of a river, is called laminar flow. I guess that's how it says it because that's about the only way I've ever pronounced it. So that's laminar flow or streamline flow. What that means is that all your liquid is going in one direction. There's no twists, there's no turns. It's just moving on down the line. Okay? And then if you come across corners or you come across obstructions, is the best way I can call it. If you come across obstructions in that same pipe, what kind of flow do you get? You get turbulent flow or chaotic flow, whatever you want to call it. Essentially, yeah, that's the best way I can describe them. Is if you've ever been on a river, you know exactly what I'm talking about. So, questions on that? And yes, you probably do need to write down those terms. They are very common, very well-used terms. So you have laminar flow, that is the smooth, glass-like flow. We all like to ride down with a canoe because then you can just paddle lightly. You have not got a real current under you most of the time. Versus the turbulent flow, which that's what you want to go down if you're whitewater rafting. Because that's where the adrenaline and the fun is. I've got a lot of y'all nodding on that. Any adrenaline junkies in the house? Got a few. Okay. And I'll say I'm actually one because I went down that with down the river with my nieces and my parents over a little bit of a summer break. It's a lot of fun. So pressure occurs when there's resistance to fluid flow. This is occurring at actuators, orifices of a pipe. So if you change the size of the pipe, or if you just change pipes, period, that can cause a change in your flow. Yeah. And that should not be values, that should be valves. I'm going to, let's change this. Valves, not values. I keep meaning to change that, and now I have. So pressure is required. So, if you ever want to move a load, you have to have the pressure to move it. Okay? So it has to be higher than what it's called to support a load. So it's easy to support a car, right? Once you have the pressure to support it, but what if I need to raise that car off the ground? My pressure to hold it, that's one thing. I have to have extra pressure put on it in order to raise it up so that I can work on the bottom of the car, right? Does that make sense? One of the things we have to overcome with that is, first of all, friction. Friction is what? Friction is friction, right? It means that you have something trying to hold it back. Because friction is part of life. Back pressure in the return line, we'll talk about that more at another point. But essentially, how can I describe this? Back pressure is one of those things that if you've never dealt with it, it's really hard to describe it and understand it. But essentially, back pressure works almost like a dam. It ends up pushing and not allowing flow through a river of pressure, okay? It is a very common thing to have. It's a very hard thing to describe beyond that. And we will be actually doing it whenever we get to lab. So at that point, might be a little easier to talk about. The energy required to accelerate a load up to speed. Think about a train. How hard is it for a train to move up to speed? You've ever gotten stuck when one's trying to move and begin moving? It takes an act of sheer will to get that thing moving, right? Well, hydraulics and pneumatics face the same thing. It takes a little bit to sometimes move something, especially if the load is quite heavy. So think about some of those big cylinders we saw the other day on the video. How hard were they working? You got a really heavy load. You got, let's say, a full bucket load of limestone. It's going to take a little bit more to move that bucket than if the bucket's empty, right? That's what pressure to remove a load must overcome. Okay? So the flow rate into a cylinder is in inches cubed per second. Area is inches squared. Velocity is of the piston is in feet per second. We don't really work with this particular formula very much. But that is how they start looking at the speed a cylinder will move. Okay? So I think I need to go back through this at some point and actually start messing with it. So area is, I think we've already talked about this, is included with a set of lines. The amount of surface within a specified boundary measured in square units. It's generally length times width for squares or rectangles, or you have your formulas that we've already talked about, pi r squared, pi times c squared divided by 4, or diameter squared times 0.785. All right, we've already talked about pressure. Now, there is a little bit more I want to touch on with pressure. Okay? Pressure is the condition of being pushed, of course. Force coming into direct contact with something. Compression is a form of force. But there's two types of actual pressure and the way we measure it. If you remember, what did I say the pressure on Earth is at sea level? 14.7 psi. That is the average pressure you feel at sea level. Okay? So, in order to compensate for this and actually figure out the pressure a system is under, okay, we have a gauge pressure which takes that 14.7 already into account when it goes to 0. There's two types of pressure. You have gauge pressure, which is generally represented as, erase some of this and give myself some space here. So you have PSIA and you have PSIG. Okay? So PSIA, that's supposed to be a lowercase g. PSIA, this is true 0. So that means you end up adding 14.7 as part of what you're seeing on that gauge. Does that make sense? In other words, it does not compensate for that 14.7. PSIG starts at 14.7 for 0. Okay? So it compensates it. Now, neither one is better than the other because at the same moment you're also just dealing with pressures, right? Now, I will say if you are at sea level, this right here does not really matter. However, are all cities and all factories sitting at sea level? None. Look at Chicago. Is that sitting at sea level? No. I'm thinking, isn't it Denver that sits up in a higher elevation too? So those cities, they have 14.7 pressure at where they are? No. The higher off the ground you are, the less pressure there is holding you to Earth. Does that make sense? Kind of, sort of, everybody? So if you stand on the top of Mount Everest, the highest point on Earth, right? You're standing on the top of Mount Everest, you are at the least amount of pressure that there is to hold you to Earth. The air is really thin up there because there's not as much gravity and force holding you to Earth. Does that make sense? Now, what the exact pressure is, I don't know off the top of my head. I don't think it's truly like majorly, like there's no gravity, but it is not going to be your 14.7. So how something that reads at absolute PSI A, it could make a difference in what you see in the system. You might have it geared at sea level to be 200 PSI. Okay? And it's an absolute pressure gauge. But when you get it up, let's say halfway up Kilimanjaro, one of the other really tall mountains, you might see a drop off in that pressure. Does that mean that your system pressure changed? Yeah, because you're actually affected by that 14.7 and the change in elevation. Is it going to change truly, miraculously, and drastically? Probably not. You'll probably see a couple PSI difference, max. So, like I said, there really is no one better than the other. So, if I give you PSI A and ask you to find PSI G, because that is a test question, worthy of the name test question, what you would be doing is, so let's say if I gave you 200 PSI A for PSI G, all that would be was what? Other way. Hold on. I'm getting myself backwards here. I'm sorry. Now you would add 14.7 to PSI A to get PSI from PSI G. So from here you're going to subtract. So it should be 196.3. I'm sorry, 195.3. Because it starts at 14.7. So that means you have to subtract that out of your absolute pressure. Does that make sense? And I think I actually did that math right in my own head. Let me double check it. 185.3. Dang it. I knew I was close. So 185.3 for PSIG. Does that make sense to everybody? Okay. So let's talk about cylinders, because these are probably one of the most common types of pneumatic and hydraulic movers. How about that? We'll call them movers. Because this is probably one of the most common things you'll find on a pneumatic or hydraulic line. They're cylinders. What we have are two parts of them. You have the bore and you have the rod. Okay? You have the bore, you have the rod. And so we use two different areas for calculating for a double acting cylinder. Because let's put it this way. If you're pushing on something, would you rather have something in the way of what you're pushing on? Or would you rather have a flat surface to push on so you can get the job done? Which can you apply more force to? Flat surface. Okay? So two different areas are used for calculating what is known as a double acting cylinder. The reason it's called a double acting cylinder is because if I put pressure on one end, it will cause it to extend. In order to make it retract, I put pressure on the other inlet. So if I want to extend, I push at the bore. If I want it to retract, I push on this side of the bore. All right, so if I'm pushing on this side of the bore, what gets in my way? The rod. The whole thing is the cylinder.
So you're saying if you push on the board.
If I push on the bottom of the bore, I'm pushing on just the bore. But if I'm pushing on this side of the bore, on the rod side of the bore, what gets in my way? The rod. And since all of this is normally cylindrical, air has a problem. Air and fluids have a problem of acting at right angles, right? They like to act to right angles. Well, if there's a rod in the middle, how easy is it to act to a right angle? You really can't, right? Because if you try and act to right angle of a circle, what happens? You kind of start slipping, right? That's why you don't push on cylinders, because you kind of just start slipping one way or another. Okay? So on the push end, whenever you hear somebody talking about the push area, you're looking at just the bore side. If you're looking at the pull area, you're looking at the rod. Does that make sense? So if you look at both cylinders, which I don't have one in here, I'd have to go get one. But actually, I've got a couple of them. Nah. Let me go get one just because it's easier to demonstrate that way. Okay, so this is your typical pneumatic cylinder. It's a double acting cylinder. How do I know? Because I've got holes on either side of the main cylinder casement that allow me to put air on either side of this. Okay? What you're seeing here on the picture is this cylinder on the inside. In here, I have a circular bore that is sitting probably right about here since it's retracted. In order to push this piston, and generally whatever this thing's connected to, it's pushing when it extends. Whenever I'm trying to get it to retract, I would put air here at the front hole. And what that would do is anything this guy is attached to would be what? I push to extend, I'm going to be pulling it when I retract it. Does that make sense? I figure a visual aid speaks of far more than me trying to sit here and talk it to death because y'all, I've done that a million times. I've tried to explain it a million times. Sometimes a visual aid works faster and easier. And thus, the visual aid. So the reason it's called the push area with the bore only is because you're pushing on this back end where that end of that cylinder is. And you're pushing whatever is attached to the front of this out. The pull area is dealing with this right here, this rod. Okay? So whenever you have something pushing that rod back using that bore, it can only push so much because it's having to move around this bore. Does that make sense? All right. So looking at this, let's talk mathematics here. Okay. In about 10 minutes, somebody remind me, let y'all have a break. So looking at these cylinders, what would be the extend and retract force of a cylinder with a 2.5-inch bore, a 1-inch rod, and 750 psi of pressure. Okay. All right, so first of all, let me kind of do it this way. So here's our bore. Here's the rod. Okay. Got my little air inlets here. So my rod is 1 inch. My bore is 2.5. I know it's a terrible picture, but it is what it is. I'm dealing with 750 psi. My formula for all this is what? Force equals area times pressure. Okay? So what do I have to find first? I have to find my areas first. All I've got right now are diameters. So we have 3 ways to calculate. What is the area of a 2.5 inch bore? We'll call it 4.9. 4.9 inches squared. I just don't want to write inches right now. All right. What about for my 1 inch rod? What's my area of a 1 inch rod? Should be 0.785 or something close to. Because 1 times 0.785 is 0.785. Okay? So I'm going to shrink some of this down because I need my area here. All right, so my push area equals 4.9 inches squared. My push, we know my pressure is 750. So what would be my force at push? Yes. 2.5 inch? 2.5 inches squared times 0.785.
Okay.
Well, that's just a faster way to do it. Because you can also do 3.14 times 2.5. Where's my squared? 2.5 squared equals 19. I'm sorry. I'm getting one of my formulas mixed up here. Oh, that's because that's not 2.5 squared. Then so you'd have to divide that by 4.9. If you were to do it by pi times r squared, that's 3.14 times 1.75, and then square that. I think that one's where everybody's having problems. I think that's not how you square that. All right, let me back that one up. I'm just trying to prove the 4.9 inches squared. All right. Yeah, somehow that worked. That's 2.5 divided by 2. 1.25. That's why that was off so badly. Okay. I don't know why I thought it was 1.75. Okay, so 4.9 is my push area. What is my push force? That is what we're looking for here, guys. Your pressure is 750 psi. So it should be 750 times 4.9, yes? What does everybody else get? That's funny because I get 3,675. Okay, I'm sorry. I thought you said 3,500 something. And that is your force, yes. So your force should be 3,675 or somewhere in that neighborhood. That is pounds. Okay. So that is just your push. Okay. That is just the push. So we also still have to find, so that's extend, as or you can call it extend. So what about our pull or retract? Now, here's the fun times. When I'm looking at pull, am I just looking at the bore? No, you gotta look at the rod too. So what you're going to end up doing is bore minus rod. So 4.9 minus 7.8, I'm sorry, 4.9 minus 0.785. What's that give me? Hmm? Mm-hmm. Because think about it like a wall. If you've got a piece of lumber sticking out of a wall and you're trying to push against that wall to push it down, right? Are you going to have as much surface area to work with when you have that piece of wood sticking out? Does that make sense? Huh? Okay, so no, the bore is your wall, okay? Let's say I'm trying to push this wall down, but I've got a piece of lumber that's coming out to here. My surface area of pushing against this wall to push it down is less because that piece of wood is sitting right there in the middle of it, right? That's why you've got to subtract the rod, because the bore, you don't have just the bore. You have the rod in the middle of it, And since the rod is cylindrical, air can't really push on that rod very well. Does that make sense? Okay. So that's why you subtract the rod from the bore, because the rod is taking up space in your wall that you're pushing against. Does that make sense to everybody? Make a bit better sense? All right. So what is my area? What is my pull area? 4.11? Okay. Yep. 4.11. And that is inches squared. What is my force? What is my force, gentlemen? So that would be 4.11 times 750. That gives me what? 3086. Okay. Let's see how close we got. All right, so my extend force, we got pretty close enough. 3,675. I think that's what the book says is 3682. Yes, it is. This little book is claiming 3682. It's mathematics, and pi is sometimes extended more on some things than others. Retract force is 3094. That's not even the right one in the book. That one's 3092 in the book. But I digress. So very close enough. Close enough you wouldn't really notice the difference. Okay? All right, so it is 3:15. So I'm going to give y'all another 10-minute break, and then we'll keep moving on from here. All right, so this is how you're calculating power. Most of this is not really anything you would use a lot of. Work is a measure of energy. Power is the speed at which energy is spent. By the way, if you ever want to know how your power bill is calculated, it's how much power are you using over time. So, you know, people talk about extreme lengths that they go to save power by, you know, cutting off, unplugging everything, cutting everything off, and things like that. So yeah, that would take care of it, but it's not as easy as what most people think. So electric horsepower. So motors are rated in horsepower. So one of the things you might be called on to do when dealing with hydraulics and pneumatics is, what is the horsepower of something? If that makes any sense. So in this case, hydraulic or pneumatic horsepower, what we're looking at is what is the pressure it puts out with the gallons per minute. We divide that by 1714, which don't ask me where that came from. I am not the one that invented the formula. But the biggest thing you have to do is multiply by the efficiency. Now, why do we multiply by the efficiency? Because nothing is ever truly 100% efficient, right? Never has been, never will be. So that might be something you want to write down in your notes to add to this particular formula whenever you look for it. Okay. All the slides? Yes, the slides are all on Blackboard. Okay. So this is a simplified version of the formula that works faster and easier. I said, everybody good? Okay, that's fine. I don't mind giving you a minute. All right, everybody good? So we have Bernoulli's principle. Now, we kind of talked a little bit about this, and it's exactly what I told y'all. Basically, this is how your shower head works. So to increase the speed of a fluid when you decrease pressure or decrease the potential energy. Okay? So the speed of a fluid increases with a decrease in pressure or a decrease in the potential energy. You'd think it would happen with an increase in pressure, but not. We'll dig into that more at another time. So how do you get water out of a garden hose to go faster? Hmm? No, the even easier way. You clamp the close. That does what? That drops the pressure right where you're at, and then when you release that crimp, how fast and how hard does that water move? All of a sudden it moves a lot faster, a lot harder, and a lot easier. Right? Hmm? Hmm? Yep. Everybody good? So then we have another law, and this is Charles' law. And what this essentially states, what is this thing? There we go. So this one is stating that temperature and volume kind of go hand in hand here. When the pressure of a gas is held constant, the volume and the temperature become directly related. So pressure on Earth is pretty much the same as we're at, right? When the temperature rises, the volume of the air, humidity, tends to go up. Whenever it's cold, the volume of the air, or the amount of humidity and everything, goes down. Make sense? So the temperature and the volume become directly related. So think pressure cooker, right? Have anybody ever used one of those? Instapot or whatever they're called. As you cook it, as you increase the temperature inside it, what happens to the internal pressure? It goes up a lot, right? However, as that food cools down inside it, what happens to the overall internal air? It condenses, thus it creates a what? Creates a vacuum. It sucks that lid down. Well, you're not supposed to do that. So Boyle's law, the volume of a confined gas at a constant temperature varies inversely with its pressure. Okay? So as the rises, the pressure falls. Is that what that's trying to say? Yeah, the temperature goes down because you have more volumetrically there. How to explain this a better way? As the temperature's going up, the molecules expand out. That's why we have so much more ability for humidity in the summer. Does that make sense? Because their air is less dense with air molecules, it absorbs those water molecules more readily. And as the temperature goes down, all the air molecules condense. Make sense? And thus it squeezes the water out of the air. Sorry, it took me a minute to try and process that back to a way that actually worked. All right, everybody good with Boyle's law, right? All right, so hydraulic or pneumatic systems are the best way to talk about them is the fact that they're much like electricity, separated into three different segments. Now, electricity, what three segments do we have? Supply, path, load. Well, in this case, we have a little bit different because we know that the lines are always going to be there to move it. We have a different set of three, but we're pretty much the same way. We have a power supply or your source. We know we already have the path, but we have to have some form of control, and we have our load. The only thing that changes is instead of having to worry about path, you're worrying about control. How am I moving that fluid from one place to another? Does that make sense? Those of you that have taken rudimentary electronics? I said, same principles, you still have a set of three things you're looking for: a source, a path, a load. Only you're looking for a source, you're looking for what controls it, and you're looking for the load. The load does the work. The source creates a way to move things to where that load is. And then you have, in this case, control instead of a path, because the path is kind of a given. Does that make sense? All right. So the power supply tends to be, well, let me back it up. All power supplies with hydraulics, pneumatics, or electricity are all based on either motors or, in the case of electricity, generators. You have to have electricity to move any of this. Now, that electricity comes in one of two forms. It can be either started off by the combustion engine, or it can be started off by an electric motor. Now, the electric motor is what you find in a permanent compressor or, why is my brain all so a compressor or pump, excuse me. All of a sudden I had a brain blank. Okay, so dealing with a hydraulic system, you have a pump. If you are dealing with pneumatics, you have a compressor. Now, electric motors you find in the permanent ones, the ones that are installed to be there forever. Y'all know what I'm talking about? You're talking about compressors that can be either really kind of smallish, they're generally in the house for good, or you have the really big ones that are bolted to the floor and really can't be moved. One way or the other. Combustion engines typically are the ones that are non-permanent. You see these at job sites for people to use pneumatic nail guns to drive nails or to drive screws, things like that, so that they can use air pressure instead of trying to use hammer and nails is one of the biggest ones I know of. If you ever see a pneumatic stapler or a pneumatic nailer, those things work gangbusters versus having to sit there and hold a nail and tap it in. It's also safer for your fingers. You save your fingernails that way. You also don't break your fingers as often. So the combustion engine is one you'll generally see at job sites, not so much in a house, unless it's connected to a generator of some sort. So you get pumps that convert mechanical power to hydraulics, compressors that go with pneumatics. But this supplies the flow of either air or fluid, of course. You have your output section, and this includes actuators like cylinders, and you also have two other types of actuators. One is what is called a rotary. This one rotates with set limits. So think, how many of y'all remember the old rotary phones? Or have ever seen the old rotary phones? Where you stick your finger in it, you dial that particular number. You stick your finger in it, move it all the way to where it needs to be, then you release. That's rotary. Well, guess what? Rotary actuators work the same way. It only rotates to a certain degree or another before it zips back and it's using a back and forth motion like that. It's not going to rotate all the way. With motors, now we do have pneumatic motors and you will be using them in lab. These have just like a regular motor, they rotate perpetually. Okay? We will be using those in lab. It's actually kind of fun. So the other thing we have to deal with is what is called the control. Now the control is meant to literally control where, how, and why everything flows and moves. Okay? It controls everything about how things move. So anything that is not power or a power supply or output is all included in this. We'll get into that more as we get into lab. So components that we have to deal with. So we have filters. Those are probably one of the biggest, most important things to get overlooked. What happens if you don't change an air filter or an oil filter? Anybody ever seen an air filter in a house that's not been changed for, let's say, 3 to 5 years? For anybody who's ever been at HVAC, that is a true nightmare because those things are so clogged up, you cannot get air moving through that system at all. Because generally that thing is so gunked up, especially here in Alabama. Think about it. Dust plus humidity turns into mud. Basically, it almost looks like you have mud caked on those things. Think about that for a minute. Ew. Okay. So you have compressors or pumps, depending upon which one you're dealing with. Compressed air can run really hot. It's not something you want to have in your lines all the time because it can degrade them. So some of them have what are called aftercoolers. We'll talk more about that another time. Some of these are kind of obvious. Reservoir versus a tank. So a reservoir or tank is mainly associated with hydraulics. Why? Because you do not want to run. If hydraulics run out of fluid, what happens? Somebody tell me what happens. It's not that it gets dirty. Everything starts burning up. It's the first thing that goes is your ever-loving pump. If you ever have run the idea because it absolutely tears it up. It burns out. What it does is it uses that fluid to keep that pump cool. Okay? Just like your motor engine uses the fluids in the motor to keep it cool, it's using the oil or water or whatever you've got it in to keep the system cooled down. Otherwise, you're going to start frying things out. Really not good in a pump because those things can be very expensive. Think replacing a car engine. Expensive. Not fun. Not cheap. Not anything you want to do. Okay. Lubrication filter, pressure regulator assembly. Something you regularly find with pneumatics. Again, lubrication filter generally tries to take any oils and stuff that you add to your system and spray it as a fine mist to be picked up by the air and carried to your parts. Directional control valves we'll talk more about later. You have relief valves and just about everything you do. Pressure relief valves are common for no matter what kind of fluid power system you deal with. Why? Because if the pressure gets beyond what a system can handle, we talked about it earlier, you put too much pressure on a system, you're going to blow all the seals out at the very least. At the very worst, you're going to damage a lot of things in that equipment. It's not a good idea. Okay. So hydraulics versus pneumatics. So hydraulic is powered through liquid, pneumatics powered through gas, of course. So some of the differences. Hydraulics are not compressible. Now, that sounds kind of like a misnomer, doesn't it? Because we're talking about how much pressure we're using on certain parts. But the truth is, it's how much force and speed we're moving it with. Does that make sense? It's not so much that we're creating a true pressure with hydraulics, because you can't. Think about, again, compressing any kind of a water bottle or anything that's got any kind of liquid in it. What is the problem with that? Is that you are going to find it very quickly kind of gives out and goes, nope, bust a seal somewhere or breaks somewhere else, and it's free to go. So it's not compressible, even though we are able to use pressure with it. Does that make sense? It in and of itself creates its own pressure, I guess you could say. Be a better way to say it. Gas is highly compressible. Only there is a point where if you overcompress gas, yeah, don't overcompress gas. There is a certain point where if you overcompress air, what makes up air? Let me start with that. What makes up the air we breathe? Nitrogen, oxygen, helium. You start creating, well, let me say it this way. Air is molecules that are not bound together, right? They just kind of hang out. As we breathe, we pull some of them in. As we exhale, we push more of them out. Correct? Okay. Now, let's say we take all the air in this room and we start to compress it. We've already said we have things like oxygen, nitrogen, hydrogen, helium. That's just four of the basics. What happens if I start putting oxygen closer to, let's say, hydrogen? What does 2 oxygen plus 1 hydrogen equal? H2O, water. If you overcompress air, you get all sorts of nasty chemical reactions starting. Not so much nasty as in they're going to destroy things, but it's nasty as in it does not play very well with your system because it can create things like water and other things that do not agree with air and metal parts. So, it's something that you do have to be aware of with air because the more you compress it, the closer those molecules become. The closer they become, the more likely they are to bond, the more it's going to cascade and cause problems. Now, you are kind of probably wondering, well, if that's true, why do we use it? Well, because it's a very cheap, easy source that we don't have to try and figure out a way to return back to itself. We just vent it. And generally, most pressures are not really high enough to do that. Okay? It really is not. It's just a possibility that it can. And it's one of those things of there's a reason why you have areas where it's going to try and pull moisture out of your system. And it's for reasons like that to try and prevent water from getting in your system. Water getting in the system is probably the biggest disaster you could have. It does not like itself. Hydraulics are very high power components, not so much with pneumatics. And it goes back to that air is pretty well compressible. It likes to be compressed. Fluid, not so much. You have very precise precision positioning with hydraulics, moderately so with pneumatics. Hydraulics tend to be very smooth movements. Pneumatics can kind of be kind of jerky. And I don't mean that they're jerks. I mean that they sometimes, spaz out just a little bit. They tend to be a little bit more quick moving. All right, any questions on that? All right, and lastly, here is our summary. So the things we've talked about, Pascal's law, the types of fluid flow, the three sections of a fluid power system, what is power, fluid horsepower, Bernoulli's law, and Boyle's law. Have y'all got any questions for me? No? All right. Then we will go ahead and end this. I'll go back later and figure all that out. If y'all don't have any questions, I'm going to stop this.